So let's start with the Gauss's law example. Let's say I have a line charge that is positive Q, like this, surrounded by another shell. Let's say it's a thin shell, so there's no thickness. That is minus 3Q of charge. So there's negative charge on this thin shell like this. How do you do it? What is Gauss's law for? Gauss's law is for finding the electric field. Okay, that's the first thing you need to know. Gauss's law is to calculate the electric field strength. I want to emphasize the word strength because what that means is it's finding E, not E vector. What is the difference? Remember, this is the magnitude. This is a lazy way of writing the absolute value or the magnitude, which is the length of this guy, okay? So in particular, this is always positive. It cannot be, if you come out with something negative, you know that is immediately wrong. So Gauss's law finds the electric field strength of something. So now, how do you find electric field strength? You need to ask yourself, is it a point charge or is it not a point charge? So if it's a point charge, you might be happy to know you already have a formula for that, right? So here you just plug in the charge of that point charge, and then you'll be able to find the electric field strength through this way. But if it's not a point charge, never use this formula. That is only useful for point charge. So what if I want to find on the left in my diagram over here, I want to find the electric field strength somewhere outside over here. What is the electric field strength? This time I cannot use Coulomb's law as I just wrote. You need to use Gauss's law. So this is how you use it. First thing I want you to do when you study this is memorize this and then also label the S, the surface. What does that mean? I'll show you what it means. First thing, before you even tackle the algebra, there's 3 steps you want to do, and all the Gauss's law problems follow these 3 steps. First step, draw the electric field lines. So it's going to be radiating outwards from the center. How do I know that? It's because of the symmetry of the problem. So it's cylindrically symmetric, right? So all the field lines should emanate cylindrically away from here. Now, how about these? I need to draw the arrow of the direction as well. So let's zoom in. How do I decide the direction of these electric field lines? Remember, you imagine a positive point charge and ask yourself which way it goes. So if I have a positive charge here, since the middle is positive, it's going to go this way. It's going to repel. So the electric field lines are going to get attracted to the surface. So within the cylinder, this is how the lines are going to point, right? Imagine a little positive point charge. Which way will it go? How about outside the cylinder? Let's zoom in to outside the cylinder. If I put a positive charge here, right, in particular, I'm interested in the electric field strength over here, right? Which way will it go? Well, it's going to go this way. So outside the cylinder, it's going to point in because the surface of the cylinder is negative. Right, so that's your diagram. So the first thing you draw is that. The second thing is you look at the Gauss's law and you write it down, which I've already done, and you solve the right-hand side and the left-hand side. You can deal with them separately, okay? I like to deal with the right-hand side first. So first, you need to decide a Gaussian surface. What that means is if you are interested in the electric field here, draw a surface that passes through here. And you want to encapsulate the whole thing because that's what this little circle means. It means you need a closed surface. It needs to encapsulate the whole geometry like that. Notice my Gaussian surface, let's call it S. It consists of 3 pieces. It consists of the left, the right, and the side, okay? So there's a left-hand piece, there's a surrounding it, right? It's the side, and there's a right-hand surface, okay? So the closed surface S comprised of S1 plus S2 plus S3. All right, so let's do the right-hand side first, it's easier. So the right-hand side, first thing you do is you copy it out exactly as it is. Everyone can do this, so do that. And then ask yourself, what's the charge enclosed? Enclosed in what? Enclosed in S. That's the benefit of writing S. So what's the charge enclosed in here? Well, there's minus 3Q here, and then enclosed in it, there's also plus Q. So there is minus 3Q plus Q. So all these are enclosed inside S. Okay, so that's done. So we can focus our attention on the left-hand side. It looks scary, but everyone can do this first step, copy it out. Now you look at this, you need to integrate. This is the scary thing here, right? So how do you simplify that? Well, S consists of 3 pieces. So make sure you break the integral into 3 pieces. Notice when you break it into 3 pieces, I no longer have this little circle around my integral because these are open surface, not closed surface, right? S1 is just an open surface, S2 is an open surface, S3, again, you don't have the lid. S3 is just the side, so again, it's just a plain surface. So you don't write the little circle. I mean, no one would deduct your point if you write it, but it's not there. All right, now let's analyze the vector. That's the second most complicated thing in this expression. So what is E and what is dA? Well, where do you want the E and where do you want dA? Well, on S1. So let's zoom into S1. Let's look over here. What's the dA? dA is you ask on S1, pick a small piece of area and then find the area vector. An area vector is always a vector that's 90 degrees perpendicular from the surface. Okay, so you pick a little surface dA and the vector dA vector is 90 degrees away from that surface. It's always pointing away from the interior like that. All right, that's dA. How about E? Well, we already drawn this, right? The electric field is pointing this way. So EDA, what's the dot product between EDA? You need to know how vectors work. How dot products work. So if they are parallel, you just have AB. If they are anti-parallel, you have minus AB. If they're perpendicular, you have 0, right? The general rule is AB cosine theta, where theta is the included angle between the two vectors. So you have normally 3 simple choices. Either this just becomes AB or negative AB or 0. Which one's the case here? The case is it's perpendicular. So E dot dA is 0 because E is perpendicular to dA on S1. How about S2? S2 is the same story over here, but this is the side of the right-hand side of it, right? So a little piece of area would point this way. How about the electric field? The electric field over here, so this is dA, but the electric field is, as I drawn with my blue lines, it's pointing this way. Again, they're 90 degrees perpendicular. All right, how about S3? S3, let's pick a little area over here. Remember, S3 is the surrounding bit, so the area would be pointing this way. And how about the electric field on S3? The electric field over here, as I've drawn, right, it's pointing this way. Which case is this out of these 3? The E and the dA is anti-parallel. Okay, so you have negative EDA, right? 0, 0, negative EDA. Is E constant? Well, absolutely not. But because the further away you are from here, of course, the E will get weaker and weaker. The closer and closer, you'll get stronger. However, around S3, if you go around here, right, go around S3, due to the symmetry, there's no reason that E is stronger on one side than the other. So E is constant as far as S3 is concerned. So as far as S3 is concerned, you can pull that out. So now you just have to integrate this. What is integrate dA? It's just A. Integrate dx is x, integrate dA is A. A of what? A of S3. Notice the usefulness of writing S3 because now you know exactly what area to look at. You want the area of S3, which is 2 pi. Let's say that is the distance r. So it's 2 pi r times the length, and that's the length, right? So it's 2 pi r, that's the circumference times the length, that's the area of S3. Okay. So now you just have to combine your left-hand side and the right-hand side together, which means 2 pi RL equals to minus 2Q over epsilon naught, and you need to solve for E, like that. The minus sign cancels out and you get something like this. Okay. So you see that it's positive, as it should be, because electric field strength always positive. Okay. All right, so that is how you use Gauss's law. Memorize this, and it's basically doing left-hand side, right-hand side, combining them. Draw your electric field lines and draw your Gaussian surface.